we're going to use examples to illustrate how we do things, right? Consider these baby weight statistics. Weight of male babies less than 2 months in the U.S. is normally distributed. Now, by the way, when they say normally distributed, they really mean approximately. Nothing is ever perfectly normally distributed, but that's beside the point. Anyway, the mean is 11.5 pounds, and the standard deviation is 2.7 pounds. I find that to be hilarious, by the way. I've got a boy, and he was nowhere close to that when he was 2 months. Anyway, they ask a series of questions. What proportion of babies weigh more than 13 pounds, right? Well, let's see what's going on here. They gave us a problem where the mean was 11.5 pounds, and the standard deviation was 2.7 pounds, right? So if we were to just sketch this number, you won't need to do this to answer a problem like this, but I just want to show you what's going on here, right? This is the mean. If we go out one standard deviation, we add 2.7 to 11.5, we get, it should be 14.2. So this is mu plus sigma equals 14.2, right? That's going to be this right here, right? So when they say what proportions of baby weigh more than 13 pounds, well, 13 seems to be basically halfway, right over here or so, right? Right, so it's saying what is this area under the curve right there? Again, remember, we're assuming the area is always 1 because we're talking about proportions here. 1 means 100%. Okay, so it looks like the proportion should be less than 50%, maybe 40% or so, maybe 30%, something around there. Okay, well, anyway, to find that out, we're just going to use Minitab. So what we're going to do is, let's do the quick and easy way first. We go to Minitab, open up a project, blank project, graph, probability distribution plot, view probability. Now, before we would leave mean and standard deviation at 0 and 1. Now we're going to change it, right? We're just going to put in what they told us. The mean was 11.5. The standard deviation was 2.7. Otherwise, we do exactly the same. We want a specified x value, we want to make sure we're set at right tail, and the x value was 13. And so that's our answer, right? About 29% or so are 13 pounds or above. Right? So we just kind of take a screenshot of this. Right? Just kind of, crop, do the usual. Right? And then that's our answer. And so let's stick this here. Now, a photo is not an answer, so I should actually write the answer, right? So for part A, 28.93%, or we could just write 0.2893 of babies, and I guess we're assuming male babies, weigh more than 13 pounds, right? All right, so use the exact same approach for part B, right? What proportion weigh less than 15 pounds, okay? Well, again, we just kind of go back to Minitab and do the same thing, right? Graph, probability distribution plot, view probability, keep that the same, but we're doing left tail, and we're doing 15. All right, so about 90%. I'm not going to bother copy and pasting the picture. I'll just say using Minitab. .9026, I think, of babies weigh less than 15 pounds. Right, that was what I said, right? Yeah. Now, what is actually happening with when Minitab does this? Well, what it's doing, and I'll write this out a little more formally on the next page. It's taking the raw scores, converting them into z-scores, and then it's doing the same sort of z-score trick that we did before, right, using the table or using Minitab, however you want to say it, because the standard normal curve is very well studied. We know all the proportions of areas to the left or to the right of all the different z-scores. Okay, so we'll use Minitab this time. Actually, let's use Minitab one more time for part C, and then maybe we'll do it by hand for part D. Okay. So for part C, what proportions of babies weigh between 10 and 14 pounds? Well, again, graph, probability distribution plot, and now we want to do 12 and 14, or 10 and 14, rather. So this one we need to be a little, I think we're okay with this one, right? We can say this should be 10 and this should be 14. I think this will give us what we want. Yeah, there you go. See that? 0.5335. So again, using Minitab, 0.5335 of babies weigh between 10 and 14 pounds. Now for part D, let me just write out what we're doing. Let me use the chart in case, just so you understand what's going on. I say, is it unusual for a baby to weigh more than 17 pounds? And the answer is going to be yes. Let's see why. Now we could just use Minitab, right? Do the same thing we did for part A, but plug in 17, right? But instead what I'm going to do is I'm going to say, find the z-score for x equals 17 pounds. And that's not going to be too bad, right? We just use the formula. Z equals 17 minus 11.5 all over the standard deviation, which was 2.7. We do that out, and that's going to be a little over 2 standard deviations above the mean. But let's see if we can, let's see if Google will let us do that, right? So we're going to do 17 minus 11.5 divided by 2.7, 2.04, let's say, right? Okay, 2.04. Right? So 17 is 2 standard deviations above the mean, right? A little 2.04 standard deviations above the mean, right? So we already know that's pretty unusual, right? That's like in the 97th, 98th percentile or so, right? But just to confirm, we're going to use the table. Oh, did not mean to do that, or that. Here we go. So if we look at the z-score for 2.0, 1, 2, 3, 4, 97.93 or 0.9793, okay? That's what we're looking at right here. Using the z-table, we see 17 pounds has 0.9793 of the data less than, or I guess I should say 17 pounds, maybe, sorry, this is a slightly better way to write it, is greater than 0.9793 of the data and less than 1 minus that, which is 0.0207 of the data. So, yes, 17, a baby weight of they say at least or more than, yeah. I'm running out of space. Of more than 17 pounds is unusual. Right? So, I guess I did need a calculator to calculate the z-score, but I didn't actually need Minitab, so I just wanted to show you that. That said, Minitab would have been easier, right? It would have been easier if I had just gone like, here, right tail, and then just make it 17, and then, But I want you to understand what we're doing. I want you to understand why it works. Okay? They give a more precise answer, but that's what we're working with, okay? So in general, what we're doing, of course, you can always just use Minitab or your calculator. It's totally fine. But what we're always doing is we are converting the raw score x into a z-score. And then we follow the same steps we did with the standard normal curve, or standard normal distribution, or yeah, I'll just say curve distribution, etc. Probably should say distribution. Let me say that. All right. Anyway, naturally we can go the other way as well, right? What baby weight is higher than 40% of the population? Now let's just draw that out to make sure we understand what exactly we're trying to find here, right? Higher than 40% of the population, we want the weight, we'll call it x, such that this area here is 0.4 or 40%. Okay. So what we can do, again, using Minitab, graph, probability. So we want to do a specified probability in this case, left tail, 0.4. And that's the answer. Oh, that's a little annoying. Looks like it's 10.82. A little tough to see there. So we'll just say 10.82 pounds is greater than 40% of the population. Okay. If we didn't want to use Minitab, then what we could have done is we could have said, okay, let's find the z-score corresponding to 40%. And we would go here, and we would go here. Where's the z-score corresponding to 40%? It's roughly here or so, right? That looks like negative 0.21, 1, 2, 3, 4, 5. Negative 0.25. And you'd say, okay, z equals negative 0.25 equals x minus our mean over our standard deviation. Just do a little bit of math right there. And this implies that negative 0.25 times 2.7 and then we're going to add 11.5 and see. So we get a slightly less precise answer, but 10.825. That's basically the same as we got before, right? Z equals 10.825. Or sorry, not Z. This is going to be x equals 10. 3, I guess, in that case, right? So slightly different from what we had before. All right, so we get that. Then also, what range of baby weights constitutes should be constitutes. Sorry about that. The middle, 70% of the baby weights. So again, let's just draw a quick picture. We want negative z, or actually, I guess I should say negative x and positive x. Right, this is the mean, which is 11.5. This is supposed to be 70%. And I think it's probably easiest just to use Minitab to do this. Graph this. Just be a little careful here. We do want to specify probability equal tails. Now remember, we don't want to put in 0.7. We want to put in 0.3. And that should give us what we want. Now, it's worth checking to make sure that your answer is legit, right? This one I will just take a picture just because it's a little more complicated. So I'll just say using Minitab. The weight range of looks like 8.702 to 14.30 contains 70% of the baby weights. And again, we're always assuming they're male baby weights. Or maybe I should say contains the middle. There you go. That's all.